Hello students, today we're going to talk about exponential functions, how to differentiate and how to integrate them. But before we get too deep into this, I want to start off briefly with talking about just some of the rules, the power rules really, exponents rules or reviews of exponents to make sure that you are brushed up and sharp, since we're going to apply them to the exponent, to the e function. Alright, so to begin with, just real briefly, remember that if you take an x cubed times an x squared, it's going to equal the sum of the exponents, which is x to the fifth. So we can do the same, apply the same property to e. So in other words, if we have e squared times e cubed, it will equal e to the fifth. So we can just add the exponents. Another of our properties of exponents would be if we have e to the a exponent over e to the b exponent, this is just equal to e to the a minus b, the top exponent minus the bottom exponent. So if we had numbers in place of a and b, if we had e to the sixth over e to the fourth, we could rewrite that in a simplified version as e squared. Now we also need to remember how to deal with negative exponents. So remember, if you have something like 3 to the negative 2 exponent, that's like placed in the fraction over 1. If we move it to the bottom of the fraction, it makes the exponent positive. So if we have e to the negative x, we can rewrite this as 1 over e to the positive x. So just move your term to the other side of the fraction, top or bottom, in order to make the exponent positive. Now a real simple one is e to the power of 0 is 1. Anything to the power of 0 is 1 except 0 itself. And then we also have that the natural log of e to the x is x. Now there's another, this has probably been a while since you've talked about this, but this was taught in college algebra. It's called the change of base rule, which we might see a little bit of. And it's a logarithm. So in other words, if you have log base a of x, such as having log base 6 of, say, 10, well, we can't put log base a or base 6 in our calculator, but what we can do is rewrite this as log of x over log of a by the change of base formula. And then we could put a 10 as our base, which would make it calculator friendly. We could also do the natural logarithm, so it would be the natural log of x over the natural log of a, which is really just a base of e, meaning we're changing the base to e. So if you had log base 6 of 10, you could rewrite this as log of 10 over log of 6 with an assumed base of 10, or you could write this as the natural log of 10 over the natural log of 6, so that you can get an estimate, a decimal value of that on your calculator. Okay, so now let's go in and start taking the derivative. So we're going to start with our formula for the derivative. These are all in your textbook. Okay, formula for the derivative of e to the x. This is a pretty simple formula, and it's really quite easy to apply. If you have d dx of e to u, the power of u, so it's again applying like the chain rule here, it's going to be e to the u again, and then you simply take the derivative of the exponent with respect to x. So it's applying the chain rule when we throw in another variable u. Alright, so here's using an example. Suppose we want to take the derivative of 6e to the x. Well, that's just 6, and the derivative of e to the x is e to the x dx, and the derivative of x is 1, so it's just 6e to the x. Let's try another one. Suppose we take the derivative, d dx, of e to the exponent of negative 2x. Okay, the derivative of e to the x is e to the x, and then the derivative of the exponent, d dx of negative 2x, which is negative 2. So we would rewrite this as negative 2e to the negative 2x power. Alright, let's throw a little bit of a trig function in here just for some fun. Let's compute the derivative d dx of e to the power of sine x. Alright, the derivative of e to the u, or e to the sine x, is going to be e to the sine x again. But then we have to take the derivative of that exponent. The derivative of sine x is cosine x. So it's e to the sine x cosine x. And you would usually put the trig function after the exponential function e. So the derivative is not too difficult. So now let's take how we would integrate. How do we integrate here? How do we integrate, say, e to the u? Okay, so the property is, if you're going to integrate e to the u du, then it's simply e to the u plus your constant. Alright, so let's apply this. I'll rewrite this on the next page so we can see it. So we just said that the integral of e to the u du equals e to the u plus c. So here's an example or two. Suppose we want to integrate e to the 4x dx. Well, in this case, we're going to let u equal 4x. So then du equals 4 dx, or 1/4 du equals dx. So by substitution, this becomes the integral of e to the u is 4x, and dx is 1/4 du, so I'm going to put the 1/4 out front, du. So this simply becomes 1/4 e to the u plus c. But remember to replace your u with 4x. And there's the result of the integration. Alright, let's try another one. Suppose we want to integrate from 0 to pi halves of e to the power of sine x times cosine x dx. Alright, so we're going to use method of substitution. Let's let u be, scroll up a little bit, having a hard time getting my pen to work. Let's let u be the exponent sine x, then du will be cosine x dx. So this will convert to e to the power of u, and cosine x dx is du. Now we have to watch out for our upper and lower bounds here. So in other words, if I have u equaling sine x and we have pi halves, then this would be sine of pi halves, and sine of pi halves is 1. So my upper limit is 1. On the lower end, u equals sine x. So if my x value is 0, the sine of 0 is 0. So I'm integrating from 0 to 1 e to the u du. So this becomes just e to the u, evaluated from 0 to 1, which becomes e to the first power minus e to the 0. Well, e to the first power is e to the 0 is 1. So the grand answer is just e minus 1. I guess I didn't have to write that again. Right, so integration and differentiation is really not too bad for the exponential function e. Okay, so now let's switch over and look at something new here. We're going to talk about exponential functions, but not necessarily the e exponential function. So we're going to look at a formula. There's quite a few of them in this section. And this one's going to be the derivative of the exponential function, but not e to the x exponential. The derivative, a basic derivative. I'll just call it of a basic exponential function. So we're talking about exponential functions like 2 to the power of x, or 3 to the power of x, or 5 to the power of x. These e to the x, we have a unique formula for it, so now we're going to use where the bottom is not e, the base is not e, but the base is pretty much an integer. So suppose we have, here's the lovely formula, and this is going to be kind of difficult one to memorize. It's a, I'm going to erase the number 1, just write the formula. It's a to the u which would be like 2 to the x, and the derivative of it is a to the u natural log of a, and then du dx. That's the property. Alright, so let me apply it. It's really not difficult to apply. So suppose we have d dx of the exponential function 3 to the x. Now realize 3 to the x is not the same as x cubed. They're very different. The exponent is where the variable is, and that's why we have to have a new formula for taking this derivative. So comparing it to the formula above, in other words, our a is 3 and our u is x. So when we take the derivative using this formula, it's just going to be 3 to the x, then the natural log of 3, and then the derivative of the exponent, which is just 1. So the answer is simply 3 to the power of x, natural log of 3. Okay, let's take one that has a trig. Let's do one that has a trig function in it. Let's compute the derivative of 3 instead of the power of x to the power of sine x. Okay, we're going to apply the same rule. So it's going to be the same thing, 3 to the power of sine x times the natural log of 3, the base, and then we have to take the derivative of the exponent. So the derivative of sine x is cosine x. Now this one's goodness, this one's kind of difficult to write. I guess we could really leave it in that order. Remember, this is 3 to the power of sine x, and I would put the natural log of 3 in parentheses, so cosine x is not confused as being the argument of the natural logarithm. Right, so it's really not difficult to apply, it's just learning that formula. Alright, here comes another formula. There's, like I said, many of them in this section. Scroll down to a new page. So here's another formula. Alright, so now instead of integrating, instead of taking the derivative, now we are going to integrate. Okay, so now we're going to integrate instead of differentiate. We're going to integrate the basic exponential functions. Now remember, e to the x has its own formula, but these are all the rest of them, such as, how do I integrate 2 to the x? How do I integrate 3 to the x or 5 to the x? How do I integrate this? Alright, we're going to have a formula. So instead of taking the derivative, now if I integrate a to the u, like 2 to the x, then it is a to the u over the natural log of a plus c. So it's just follow the formula. So for an example, suppose we want to integrate 2 to the x dx. Then it's going to be 2 to the x over the natural log of 2 plus c. That's all there is to it. So let's do another example. Throw a trig function in here. Suppose we're going to integrate 5 to the power of sine x times cosine x dx. Okay, so this one looks a little more difficult. It doesn't quite look like the 5 to the x or the 2 to the x. It has your trig functions in here. But let's do a little bit of substitution. Let's let u be the exponent sine x. Then du would be cosine x dx. So this would now be written as the integral of 5 to the power of u du, which is more of the a to the x. So according to our formula above, which we can still see, this would be 5 to the u over the natural log of 5 plus c. But I need to go back into my x variable, so this would be 5 to the power of sine x over the natural log of 5 plus c. That would be your answer. So again, these are really not difficult to apply. There's just a bunch of them. Alright, so these are your exponential functions. So now let's talk a little bit about our logarithms. Let's come out of the exponentials and let's go to the logarithms. So a little bit of a review of logarithms before we try to differentiate them. Okay, So we have some basic properties. So in other words, if we have log base 10 of 1,000, it equals 3. This is the logarithmic equation. Its equivalent exponential equation is to take the base to 3, power of 3, which will equal 1,000. So in other words, 10 cubed equals 1,000. All right, now that we see the pattern, if we have log base a of a to the x, it will equal x, because a to the power of x is a to the power of x. So for instance, if we have log base 5 of 5 to the x, it will equal x. All right, here's another one. I guess I could number these. Suppose we have a to the power of log base a of x. That's kind of an interesting one. That equals x. So using numbers, it makes it a little more clear to see. That means 4 to the power of log base 4 of x will equal x. Okay, and we've already discussed the change of base formula. So now that we have a little bit of a review of kind of the patterns in logarithms, let's go in and let's look for the formula in which we're taking the derivative of the logarithm. Okay, so we did all the derivatives of the exponentials. Now we're going to take the derivative of the logarithm. All right, so here's the formula. The derivative of log base a of u is equal to 1 over the natural log of a times 1 over u du dx. All right, let's take a look at an example. Suppose they ask us to take the derivative of log base 5 of 4x plus 1. All right, the derivative is 1 over the natural log of a, which is the base, times 1 over u, which is the argument of the logarithm, and then the derivative of the argument, so the derivative of 4x plus 1 is just 4. So this answer is 4 over, and you can probably put in parentheses, the natural log of 5 times 4x plus 1. That would be your answer to that derivative. Now, we're going to take the derivative, and we're also going to do an example of integration. You're not going to see very many of these, but I'll do one real quick, also in this set. I think I'm going to need a little room, so let me go down a little further. It's not a new formula. It's really just using the method of substitution. So, suppose we want to take and integrate log base 2 of x over x dx. And we do not have a new formula. Well, the first thing we're going to do is go ahead and use the change of base formula on the numerator. So this is going to be log of x over log of 2, that's the numerator rewritten, divided by x dx. Well, actually, if you change that base to e by using the change of base, then this would become the natural logarithm, which is a little easier to work with. So this is also the natural log of x over the natural log of 2 all over x dx. Now remember, the natural log of 2 is a constant. That's just a number. There's no variable in that. So I can pull out 1 over the natural log of 2, leaving behind the natural log of x over x dx. It seems like a lot of work. Okay, that's where the change of base comes in. We changed it to the natural logarithm. So now let's come over here and use substitution. Let's let u equal the natural log of x. Then du will equal 1 over x dx. So now we have this constant out front, 1 over the natural log of 2, and we have the natural log of x is u, and then du is 1 over x dx, which is This is the 1 over x dx, so this is just u du. Well, that makes it pretty easy. So now when we actually do the integration, don't forget the constant out front, and this would simply be u squared on 1/2 u squared, and don't forget your constant. Sorry, I got distracted there for a minute. I'm at home. Okay, so if I clean this up, this is going to be 1 over 2 natural log of 2 u squared plus c. Now remember, this function was given to you in terms of x, so your answer needs to be back in x. So up here, remember, u was the natural log of x, so this answer is 1 over 2 natural log of 2, and u is the natural log of x squared. There it is. So there was no new formula. We really just used the change of base formula to rewrite this as a natural logarithm, and then we just used method of substitution to integrate. I know that's a pretty long recording, but that is the end of this section, all in one recording, and I hope that's helpful.